Decomposing videos into layered representations is a foundational challenge in computer vision, one that powers everything from cinematic visual effects to interactive video editing. At its core, this task seeks to separate a video into distinct components: the foreground object, its associated visual effects like shadows, reflections, or smoke, and the background. This is known as the Omnimatte problem, a task that, until recently, required slow, multi-stage optimization pipelines that were computationally expensive and often failed to preserve subtle effects. But today, we introduce EasyOmnimatte, the first truly end-to-end video Omnimatte method that eliminates the need for these complex, time-consuming workflows. Instead of running multiple passes of optimization, EasyOmnimatte performs full decomposition in just seconds, all while producing higher fidelity results than any prior approach. So how does it work? The key insight lies in repurposing a powerful pre-trained video inpainting diffusion model. These models are trained to remove objects and their associated effects, for example, erasing a person from a scene while also removing the shadow they cast. This suggests they already possess an internal understanding of what constitutes a foreground effect. But here's the paradox. If you naively fine-tune such a model to predict an alpha matte, the transparency layer that defines the foreground, it fails to capture those same effects. Why? Our systematic analysis reveals that the model's perception of effects is concentrated in specific layers of its architecture. In particular, the middle stages of the diffusion transformer blocks are highly sensitive to effect cues like shadows. But when you apply low-rank adaptation, LoRA, across all blocks during fine-tuning, the model overemphasizes the main task of alpha prediction, suppressing the weaker, effect-related signals. This is where EasyOmnimatte's innovation shines. Instead of a single unified model, we train two complementary experts, both built from the same pre-trained backbone, but with distinct roles and fine-tuning strategies. The first is the effect expert, which applies LoRA only to the final stages of the architecture, the very blocks where effect perception is strongest. This allows it to capture the coarse structure of both the foreground and its associated effects, even if the alpha matte boundary is still blurry. The second is the quality expert, which applies LoRA to all blocks. This enables it to refine the alpha matte with high precision, sharpening edges and removing noise, but at the cost of losing effect awareness. Now here's the clever part. During diffusion sampling, we don't run both experts in sequence. That would double the cost. Instead, we use a dual expert sampling strategy. At early high-noise steps, when the image is still unformed, we use the effect expert to generate a coarse, effect-aware prediction. This ensures that shadows and reflections are properly seeded into the output. Then, as the noise level drops and the image begins to stabilize, we switch to the quality expert to refine the matte with pixel-perfect accuracy. This hybrid, stage-aware approach achieves the best of both worlds. It preserves the subtle, complex effects that other methods miss, while still delivering a crisp, clean alpha matte. And critically, it does so with roughly half the computational cost of running two full diffusion passes. We evaluated EasyOmnimatte on a wide range of real-world videos, from people walking through dynamic environments to complex scenes with smoke, reflections, and rapid background changes. Compared to state-of-the-art methods like Gen-Omnimatte, which require minutes of test time optimization, EasyOmnimatte runs in under 10 seconds, and with superior results. Qualitative comparisons show the difference clearly. Gen-Omnimatte often suffers from color bleeding, background artifacts, and failure to preserve shadows. In contrast, EasyOmnimatte maintains foreground integrity, cleanly separates effects, and produces temporally consistent results. Quantitative metrics confirm this. On PSNR, SSIM, and FVD, Frachet video distance, EasyOmnimatte outperforms all baselines, including learning-based matting methods like BGMV2 and MatAnyone, which struggle to generalize beyond human subjects and fail to capture effects altogether. Human evaluations further validate our claims. In a study with 28 participants assessing 20 challenging videos, EasyOmnimatte received the highest scores across all criteria: foreground integrity, effect harmony, and temporal consistency. Ablation studies reinforce the design choices. Removing the attention masking between branches corrupts the background. Applying LoRA to the wrong stages degrades effect capture. And using only one expert, either effect or quality, leads to trade-offs. One captures effects poorly, the other lacks precision. But when combined through our dual expert sampling strategy, the results are synergistic, achieving a new state-of-the-art in both quality and efficiency. One of the most remarkable aspects of EasyOmnimatte is its ability to generalize from synthetic training data to real-world scenes. We trained exclusively on videos with programmatic shadows, simple, stylized, and highly controlled. Yet when tested on in-the-wild footage with natural reflections, dynamic lighting, and complex smoke, the model still performs exceptionally well. This suggests that rather than memorizing synthetic patterns, EasyOmnimatte has learned the underlying principle of foreground effect separation, a true understanding of visual semantics. Of course, the method is not without limitations. Since it relies on the underlying inpainting model, it inherits its weaknesses. If the base model fails to perceive a shadow or struggles with occlusions, EasyOmnimatte cannot recover it. But as video inpainting models continue to improve, so too will this approach. In conclusion, EasyOmnimatte redefines what's possible in video decomposition. By leveraging the generative priors of diffusion models in a principled, dual-expert way, It transforms a once slow, multi-stage problem into a fast, end-to-end pipeline, setting a new benchmark for both performance and practicality. This isn't just an incremental improvement. It's a paradigm shift in how we think about adapting large-scale generative models to complex, detailed vision tasks. And it opens the door to new possibilities: real-time video editing, seamless compositing, and creative workflows that were previously impossible at scale. If you're working in visual effects, video editing, or AI-driven content creation, this is the future. And it's already here,